Thank you very much. So first of all, I would like to thank the organizers for organizing this meeting here in Cambridge, and also for having me here and giving me opportunity to show you our latest results on single ions and Cavity-QED. So this work is concerned with interfacing a single ion with a quantized light field in an optical resonator. And most of you are probably familiar with the fundamentals of that. But in a nutshell, it's basically the following. We have two mirrors which single out a single mode of the electromagnetic field and a single particle in there, say a two-level system to start with, interacts with this light field with a coherent coupling strength G. And this fundamental mechanism of the single-photon field or single mode field and the single two-level system gives then rise to this Jaynes-Cummings Hamiltonian, which governs the fundamentals of all the processes that we're looking at here. So in principle, you have the atomic level splitting here with the SZ operator, and you have the coupling of the atomic excitation to the creation and annihilation operators of the photon field. Now, the crucial part here is that the strength of this coherent coupling between the single emitter and the photon field depends on how well you can confine the single mode, the single photon into this single mode here. And so it depends on the mode volume of this resonator in the way that it scales like the square root of the mode volume. And then, of course, times the dipole matrix element, because we look at electric dipole transitions here. Aside from this coherent coupling that is fairly well captured in this Hamiltonian, there are, of course, dissipative processes in this problem. And there are decay rates of the excitations of both the atomic excitation as well as the cavity field excitation. So the atomic excitation decays with the rate gamma into all the other modes of the electromagnetic vacuum, and the cavity field can decay with the rate kappa through the cavity mirrors, essentially. And this rate kappa is the rate that we actually need in the experiment to detect any photons coming out of the cavity on our single photon counters. So in order to have a time evolution of the whole system that is governed by quantum dynamics, you want to have this coherent coupling strength here to be a large quantity. Particularly, you want to be larger than gamma. That's the rate at which the atomic excitation decays. And ideally, it's in some competition with kappa. This depends on whether you want to extract the photons very rapidly, then you'd want to have a large kappa, or when you want to look at this in a confined system, then you want G to be larger than kappa. So here's a choice, but this can be adjusted just by the reflectivity of the mirrors, essentially. So this Jaynes-Cummings Hamiltonian and overall this atoms in cavities have long been studied as a model system or an elementary model system for system-bath interactions, because if you pump the cavity or if you leak out the cavity, then you couple to the external world, and this forms a big, usually Markovian bath. The cavities can be used for efficient single ion detection, because effectively with this G you can enhance the coupling to a radiation field larger than the atom would interact with the field normally, and this can also give rise to possibilities to non-destructively detect atomic states in such a Cavity-QED setting. It can be used to create single photons coming out here at the rate determined by kappa, and so these cavities have also been used and proposed as networks for quantum as network nodes for quantum networks. And finally, of course, you're probably familiar with the large number of proposals of how such a system can be used for quantum computing at high rates, computing rates, because the timescales are now set by this coherent coupling strength G, and not like in ion traps, usually by the trap frequency in motional gates, for example. So G can be much larger than typical trap frequencies. So this is sort of the overall setting in which our experiments take place. And now let me, okay, there's one more motivation actually. So this is maybe the dream of what one would like to achieve. to build networks where you can communicate with single photons between single emitters here, where the photons are the carriers of the information, and you have these nodes where you process information. And if you have atoms in these in these nodes here, then you can actually ensure some scalability, because you know that the resonance frequencies in all these nodes are the same, and you can guarantee that if you emit a photon here, you can actually absorb it there. So this all sounds very promising. So what are the problems that we're facing? Part of these problems have already been discussed yesterday in particular, namely the question to as what happens when you bring atoms very close to surfaces. I just said the coupling strength that we can achieve depends on the mode volume of the cavity. So that its advantage is to make the cavities very small, ideally, say, hundreds of microns in length. But this means we bring a dielectric surface very close, say in 50 microns, 70 microns distance to a single ion. And there have all these data have been collected on how heating rates and ion traps scale when you reduce the ion electrode distance with this d to the minus 4 power law here, and particularly when you reach regimes where your electrode distance on the order of 100 microns, then this gets very bad. And of course, these data were collected for metallic electrodes, and now we're talking about dielectrics to bring close to the ion. So this could be quite devastating. And in fact, most of the experiments with ions and cavities so far have probably for this reason looked at cavities which were rather long. So let's say centimeters, or at least many millimeter long cavities. They have been experimented at the MPQ and in Sussex and Innsbruck and Aarhus, MIT, JQI, and other places probably. In contrast, with neutral atoms, people have worked already with very short cavities, so 100 micron long cavities, because with atoms you don't have this charging effect. The atoms have the disadvantage that they live in there only for a short amount of time. So they live there only for a second or a few seconds. So if you, in the long term, want to interconnect several of these nodes, then of course the question, how often can you have simultaneous trapping in all these different nodes, plays a role, and that's why I think ion traps are much more favorable for this goal. So we've addressed this question here. We've tried to address this question by shrinking the size of the mirrors as much as we can. So making the mirrors really tiny, and the smallest mirrors which currently I think are available and to very good quality are simply the end facets of single mode optical fibers. So in collaboration with the group of Jakob Reichel at ENS in Paris, we've machined end facets of the optical fiber. So here you see the optical fiber, diameter is 125 microns. The bright spot at the center is the core of the fiber, and the rest is the cladding. So this is machined by hitting it with a CO2 laser at the very end. And the CO2 laser gently melts the end of the fiber, creating a concave surface. And right at the center, it's to a very good approximation a parabolic surface. We then put a highly reflective coating on the end facets of the fibers, which at the moment we're working with coatings which provide a finesse of about 20,000. But this is sort of purely a choice of us. We didn't want to have too high reflectivity to actually extract the photon still from the system. So we take two of these fibers. They have a radius of curvature here of maybe 300 microns, plus minus 100 or 200 microns. We put them end to end, and this forms a nice Fabry-Perot cavity. And in fact, it looks like this. So we put these fibers into stainless steel sleeves, which we cone down a little bit on a lathe. And the fibers are just in here, almost flush with the surface of these stainless steel sleeves. And the spacing here is 160 microns. But we've played around with various distances. If you make the distance too large, then the finesse drops because of diffraction losses from these mirrors. But anything up to 200 microns works relatively well. So here's a photograph of the actual setup. Here are the stainless steel sleeves. You can, if you look very carefully, you can see the gap between the ends here. And one of these sides is mounted on, or actually this one is mounted on a shear piezo, so we can adjust the length of this cavity. Our design parameters with respect to the first slide I showed you is 6 megahertz for G, 25 megahertz for kappa, and gamma is determined by the atomic structure. In our case, it's 2 megahertz. I will show you in a minute which level scheme we're using. As for the ion trap, we're using an end cap trap, which consists of 2 electrodes. These are tungsten wires, which are etched down to a very tiny tip here, so we have maybe 1 or 2 microns radius of curvature at the tip, and the spacing between the electrodes on the order of 100 microns. So it actually sticks in between these sleeves which carry the optical cavities. The cavity assembly as such is mounted on a 3-dimensional translation stage, and we can move it around and overlap it with the single ion. So here is sort of a more a sketch of this which shows a little bit the surroundings as well. These are just compensation electrodes which we use for compensating excess micromotion. And here is the cavity around the ion trap. And the typical experiment works in a way that we retract the cavity, we load the ion into the end cap trap. So here's the composite image with a single ion between the shadows of the end caps. Then we balance excess micromotion and all the tricks. We cool the ion down to Doppler temperature, and then we bring in the cavity on the assembly and overlap the cavity mode with the ion's position. So this is an old picture. So in this version, there was not yet the cone on these sleeves, and you see the access for diagonal beams is quite a bit limited here, but we've improved this now.
So when you bring in the cavity, you
yep.
have to reshim, I assume,
Yes. Yes. So what happens when we move in the cavity? Basically, we crank up all the laser power that we have into these beams, Doppler cooling power and repumping power. We see that the ion gets displaced quite a bit. It moves significantly out of the focus of the camera because the trap gets very asymmetric when these sleeves are just displaced by 1 diameter essentially, because they are grounded. But when they're in place again, the ion moves back to the original position. We have then to recompensate the excess micromotion because probably they're slightly charged. But this is very stable, actually. Right, and now in this configuration, we then have the single ion interacting with a single mode field here of the cavity. We do these experiments with ytterbium plus, and that's the level scheme of the relevant energy levels here. So it has we have the strong cooling transition S to P at 370 nanometers. We did not quite dare to build a cavity on this transition. We instead built the cavity up here on this repump transition at 935 nanometers because the coatings are better, the fibers are better, and to get started, this seemed to be the safer choice. So, but the ytterbium offers this nice lambda scheme here, which can be driven by this coupling laser at around 300 nanometers, and then into the empty cavity mode that completes the cavity simulated 2-photon process. And the success of such a lambda transition here could be monitored, say, on this transition by the presence or absence of fluorescence. There is another reason why we chose this transition, because this wavelength is very convenient for different purposes. I will come back to that in the second part of the talk. Okay, so first of all, we had to do bits of spectroscopy on this transition because this was not yet really mapped out. So we built a laser source here based on some frequency generation of a Verdi laser at 532 nanometers and a diode at 670 nanometers, which has generated this light. And then we scanned across this transition using the shelving, so monitoring the fluorescence on the blue, and found out the resonance transition here. We measured the frequencies for the various isotopes, and we could actually see that we can laser cool on this transition as well, which is quite nice because this excited state here has a 4 megahertz line width, so this gives you a lower Doppler temperature when you actually laser cool on that transition. That's shown here. Okay, but as a next step, then we were looking at the cavity. We bring the cavity in, and then we have to find somewhere where the cavity mode is. So we move the cavity around. we pump the cavity through the fiber, and we measure the repump efficiency. So we first pump into the D3.5 state, then we bring the cavity in, which is pumped with a 935 light through the end of the fiber, and measure the repump rate back into S. And then you can map out the mode profile of the cavity. So this is now taken here in 1 micron steps, essentially. And if you take the cross sections, you see the Gaussian mode profile of the cavity, which has a waist of 6 to 7 microns, which is pretty much what we expected from the measured radii of curvature of the fiber cavities. Then, essentially using the same technique, but just scanning the other direction, we can also map out the standing wave inside the cavity, and we see the standing wave with a contrast of around 40%, which is a bit lower than what we hoped for. We don't know exactly where this comes about from, but we suspect that it's probably residual micromotion, since in this axis we can compensate the micromotion not very precisely when the cavity is around. But nevertheless, so we have a relative uncertainty of the ion's position relative to the cavity standing wave of around 100 nanometers. But I think this is something we should be able to improve in the future. All right. Now, with respect to the coupling strength, we wanted to measure how high the G of the cavity really is as compared to our design parameters of 6 megahertz. So for this, we then drove the coupling transition up to the D3.5 state and monitored the transition into the D3.5 state here. And we did this with the cavity and without the cavity. So when the cavity is not there, then you just measure the lifetime of the excited state and the branching ratio into D3.5s. And we measure this as the depletion of the S1/2 ground state. So with no cavity, we get this decay. And when we put the cavity in on resonance with this transition, the cavity gives an enhancement of this decay rate due to the Purcell effect, how it's called, or due to the coherent coupling strength. And then the depletion of the S1/2 state is actually faster when the cavity is resonant. And from this difference here, we can then extract the G, the coupling strength of 3.6 megahertz, which is larger than the spontaneous decay rate, which is 2 megahertz. The decay rate of the field is 2 megahertz. So that's the first time this has ever been achieved with trapped ions, that the G is larger than gamma. And this G here is actually, it's smaller than the 6 megahertz that we anticipated, but if you take into account that we have this 40% contrast here, then this is about what you expect. Yeah, so we can see that this cavity indeed does what it should do. So we see the enhancement of this 2-photon transition with the empty cavity mode due to the Purcell effect. Now, from then on, we were investigating how can we extend this into a single photon source, because this is sort of the ultimate goal. Is if you want to build these networks, then you have to convert the atomic excitation into photons, which actually travel out. And so for this, we used a scheme that we initialized the ion in the D3.5 state. We did this now without the 297 laser. We just used the 370 and relied on the spontaneous decay here into the D3.5. Then we went in with a very short pulse, 2.5 nanoseconds, on this transition from the side, and measured the photons coming out from the cavity mode. And this is not an extremely efficient process, because the branching ratio here is 98 to 2. So in many cases, the photon actually decays down there. But nevertheless, we achieve a single photon production efficiency of 5% into a single mode fiber. So that's the nice thing about this setup, I think, that whenever we see something here, this is directly fiber coupled, because the cavity mode here has a 70 or 80% coupling efficiency really into the propagating mode of the fiber. We then put up the Hambry-Brown twist setup here, put non-polarizing beam splitter, 2 photodiodes, measure the G2 correlation function, and we indeed find the suppression at 0 time, which signals that indeed we have single photons coming out from our ion in the cavity. We can also time resolve the shape of the photons coming out. So essentially the same scheme. We then average many repetitions of that. So this runs at a 250 kilohertz rep rate. We average for 4 minutes approximately, sum up all the photons, and then we see this the decay here. The gray shaded curve that you see here, that's the residual of the excitation pulse that comes out and is a background on the photon counter. So for the G2 measurement on the previous slide, we only took the latter half or the latter part of this this time distribution here. So as it was already indicated here, in order to avoid having the stray light from the excitation pulse disturb the photon correlation measurement. Okay, so we get out the single photons and we see their shape. They're relatively sort of this shape is relatively well determined by the 40 nanoseconds lifetime of the excited state. We can then go on and look at correlations between the spin states of the photon and the spin state of the ion and the polarization state of the photons. So for this, we make use of the Zeeman substructure of the D3 half state and the excited state. This is a D3 half state. This is a J equals 1 half state. So using optical pumping with pi light and sigma minus light, we can initialize the state here, which is a dark state, as a pure state. Then we do our short excitation pulse, again the 2.5 nanoseconds, into the excited state. From there, if it stays within this manifold, it can decay with a matrix element of 1 over square root 2 back into the original state, or 1 over square root 6 into that state. I should say there is a magnetic field which is oriented along the direction of the cavity. So what comes out of the cavity is either sigma plus or sigma minus polarized. And also I should mention there's of course a probability of decaying back into the S1 half ground state. But those events are omitted here. Then, so we then put a polarizing beam splitter and a half-wave plate here, set up 2 photodetectors, and measure the correlation here, which tells us about the polarization state of the single photons coming out. And then we can set this either to sigma plus or sigma minus or anything in between. And simultaneously, we can then read out the atomic state after the detection of the photons by again shining in pi and sigma minus light, doing optical pumping back into S1 half. If the atom ended up in the up state, then we see fluorescence on the UV transition. If after the emission the population ended up in the down state, then this transition remains dark. And with this information, we then can correlate the spin information with the polarization information, and we get out this curve here, which signals the correlation between the internal state polarization and the photon polarization. I should say that this at the moment is only measured in one basis, so there's not yet a proof for spin-photon entanglement. For this, we would have to rotate these bases and measure again. This is a bit tricky with this level scheme. We're currently thinking about ways of doing that, but this is not as straightforward as in some other level schemes. But nevertheless, we see the classical, or SZ, sigma Z spin-photon correlations here quite nicely. Okay, so much for the characterization of our ion cavity interface. And now the question is a bit, if you have something like this at hand, what can you actually do with it? And as I said in the beginning, one of our goals, in sort of long-term goals, is to go into networks of ions in cavities. One may ask the question: what kind of networks do we actually want to study? There has been this beautiful experiment in the group of Rempe just last year, where they worked with neutral atoms in cavities, and they could actually show that they could do state transfer, teleportation, and so on between these two systems in a very nice and efficient way. But sort of even in this elementary network, you already deal with a hybrid system where the different qubits that you're having that serve different purposes are of a different physical nature. So when the stationary qubits here, which are used for memories, they're atoms, and the flying qubits going from there to there, they're photons. So is already a system where it's dedicated. The roles of the photons are dedicated, and the matter of the photon is dedicated. The matter of the qubit is dedicated or determined by this purpose. So and so far in all of these systems, the focus has been on interfacing identical quantum systems, so pairs of ions, pairs of atoms, and so on and so forth. But the question is whether we can actually extend this scheme also to unlike qubit systems. And in particular, we're interested in asking the question whether we can combine this with solid-state qubits. Solid-state qubits are nice because usually they have a very rapid control over them. It can be even electrical control. You can have electrical optical interfaces in there. However, they have usually very short coherence times yet. And if we could interface them with trapped ions, and which have the long coherence time, this could be a nice match where you have sort of a processing region which is very fast and a memory which is slow but has a long coherence time. So when you look through the table of possible qubit systems, so here are trapped ions and neutral atoms, which are well ahead in terms of coherence time over all these solid-state systems like superconductors, NV centers, and quantum dots. But nevertheless, since we have this optical interface, we wanted to see whether we can actually achieve optical coupling between our single ion and a solid-state system, namely a semiconductor quantum dot. So I'm talking about this last row here. So these are optically controlled semiconductor quantum dots. They are relatively well under control. So in the groups of Yamamoto and Imamoglu, they have actually shown spin-photon entanglement in these dots already. And this could be a good starting point for building a hybrid network. So these semiconductor quantum dots, just a brief introduction because I learned about this myself relatively recently, is roughly the following. You have a semiconductor heterostructure here. You have a gallium arsenide layer. On top you have an indium arsenide layer which has a smaller band gap. And if you put the right amount of indium arsenide on top of that, you have these little islands forming in the self-assembly process. And these are quantum dots. They're maybe 10 nanometers or so in size. And they can contain single electron spins. On top of that, you put another gallium arsenide layer. And then you put a titanium film here for electrically contacting because you want to tune them electrically. And then you put up a solid immersion lens on top for photon collection. Underneath, you just put a standard stack of Bragg reflectors so that the photon emission goes upwards. In reality, this looks like that. So here's your chip, and there's the solid immersion lens. And if you zoom in, you see there is a gazillion of these little dots forming in this spontaneous formation process. They all, if you excite them, they all somehow light up. And every one of them is a nice single photon source. And if you take the G2 function of that, you see a nice suppression of G2 at 0 time. The downside is that they're all different, right? They all have slightly different resonance wavelength. So if you want to interface it with a single ion, you have to pick the right one. In terms of what's going on there internally, this looks roughly the following. So you have here the growth direction that was the vertical direction in the previous graph. You have the bands, so that's the gallium arsenide with a larger band gap, indium arsenide, smaller band gap, gallium arsenide, larger band gap, and these wells here, that's the quantum dot. So in the normal conditions, for a neutral quantum dot, if there is no light, if there's nothing, it's just a plain dot. And if you shine now in light, you can create an electron-hole pair. You create the electron in the conduction band in an s orbital and the hole in the valence band in a p orbital. So these are your quantum states S1 and J3 for electron and hole. These two together, they form an exciton, which remains localized at the dot. And the exciton quantum states are just the sum of the sz of the electron and the hole. So you have 4 exciton states, -2, -1, 1, and 2. And you have a ground state which has no exciton. And since we drive dipole transitions, only these 2 excitons are bright, and these 2 here, they're dark. And these semiconductor quantum dots here, they have a typical emission wavelength in the range of 920 to 980 nanometers, which is very convenient if you work with the terbium. As I said, we are at 935. So if you find the right one, you could have the hope of having the quantum dot talk to the ion. With regard to solid-state single-photon sources, these are probably the best and most advanced systems that there are today, because they are essentially Fourier limited. So the radiative line width is really the inverse of the excited state lifetime. The line width is around 280 megahertz in this case. Plus, since you have the exciton states which have some SZ component, you have magnetic field tuning, and the G factor is the same as atomic G factors usually. So you get a magnetic field tuning of about 10 gigahertz per Tesla. The downside of this is all of this has to take place at 4 kelvins, and in our case at around 4 Tesla of magnetic field. So here is our setup for this, for something which maybe should be more like towards a hybrid quantum network. Here's our ion in the fiber cavity, and here is the quantum dot in the groove of Meta-Atatürre, who's next door or down the hall, in a bath cryostat, 4 kelvins, 4 Tesla field, as I said. And the basic principle of the experiment is we take the laser, we excite the dot, we read out the photons, send them through 50 meters of optical fiber from one lab to the other lab, feed this then into our fiber cavity here containing the single ion, and then we see whether we can sort of transfer the excitation from the quantum dot over to the ion, so whether we can absorb the photon with the ion. And so here's the scheme. This works at 200 megahertz rep rate, 1 nanosecond pulse duration for the excitation. Then the photon travels over. We prepare the ion in D3.5 and inject the photons onto the cavity mode, measure the spontaneous decay down here, again by looking at the cycling transition S to P. And here's the data, so that if you search long enough for the right dot, if you tune the magnetic field right, you can actually see that you get absorption. So here is the gate time for which we gate the ion active in this state. And here's then the absorption probability integrated over this gate time. So for about, if everything's resonant, after 1 millisecond, we get about 50% absorption probability integrated with this rep rate. So in 1 millisecond, this means, on the other hand, that we get about 130 photons onto our cavity, which lead to this absorption probability. So this works. That's the great news. That's I think the first time that a solid-state quantum system and an atomic quantum system interact with each other at the level of single photons. We can then study the absorption probability as a function of the ion of the quantum dot driving power. So when we put more and more photons into the quantum dot excitation, we see that actually our absorption probability drops down here. This is simply because that the emission of the dot goes into a broader and broader line width, and we absorb less and less of that. And finally, as what I think is a very nice measurement, we can actually use the ion to scan the full emission spectrum of the quantum dot. Again, this is single photon emission, single photon absorption. And we see down here that the tuning spans roughly 8 gigahertz. And you see the sharp coherent scattering peak from the dot. And below that, you see the Mollo triplet of the dot excitation. And this is a few hours integration time here, but nevertheless, I think it's quite an astonishing result. Okay, so let me come to the summary. So I've showed you our experiments, Cavity-QED with a single ion. So how we built these cavities, how we use them. I've shown you our single photon interface, where where we extract the photons from the ion, and we see the correlations between polarization and ion spin state. we can now, or we will now want to extend this to building networks of cavities and see whether we can perform some quantum networking in that. And finally, I've shown you the direct coupling between a single ion and the semiconductor quantum dot. And in the long term here, the question is whether we can obtain entanglement between the atoms and the dot. That's quite a step from now still, since at the moment our dot has no spin degree of freedom yet. So we would have to inject the single electron first, create a spin state in there, and then being able to entangle this spin state with the ion eventually. Okay, so finally let me thank the people who actually did the work and our collaborators. Hendrik Meyer and Matthias Steiner were the PhD students on that project. The fiber cavities were built in collaboration with Jakob Reichel at ENS, and the quantum dot work is in collaboration with Meta Atatürk in Cambridge. And well, Michael already yesterday mentioned the new training network that we're having, so I just want to mention it again. Applications are welcome there, and we get some funding from these agencies. Thank you.
Thank you, Michael. Yeah, please.
Michael, so I just have a question on your the efficiency of getting 935 photons. You said it's 5% coupling in the fiber, but there's also is it 2% branching ratio also because the 297 fluorescence?
Yes, but this is enhanced by the cavity coupling strength. Yes. Mm-hmm.
So if you create whatever the bracket state, if you create that state at
Yep.
time 0, what's the probability that you will get a click, or that the photon will get through the fiber at 935? Is it
That's 5%. Yes.
That's 5%. Okay.
Yes.
So
And then we
sort of includes everything.
Yes. Well, not detection efficiency. Right. Detection efficiency is another 10%
Sure.
and so on later on.
It's
Yes.
into the fiber though.
Yep.
Yeah.
Mm-hmm.
Thanks.
So this is related to John's earlier question. Do you see any effects in the optical cavity when you retract and reset the fibers, or maybe if they droop over time or anything like this?
Well, the cavity is more or less a monolithic assembly on top of this translation stage. The translation stage is crap. It's an AtoCube system, and we just see it drifting and not being precise enough, and so this could also limit maybe our visibility of the standing wave. But aside from that, we don't have to compensate micromotion again. So if we retract and go back, this remains stable. Yeah.
So I'm kind of curious, and this is related to quantum dot work, where your sort of prospects are in the trion domain, so the charged quantum dot domain, particularly for this impedance matching problem. I mean, obviously, a lot of photons are making their way to your ion, but of course your ion is much narrower. So
Well, everything from the photons that go onto the cavity, we absorb 1% from the dot.
right, so I'm sort of curious what techniques you're going to aim for improving the bandwidth matching.
Filter the dot photons.
I
think there is no smarter way than that.
No, sure there is. With the trion, you can. I mean,
But the trion has the same line width.
no, you can use lambda transitions. That's single photon source.
Ah,
You can slow down the photon.
I see. Okay. Yes. You could do that. That's true. Yes.
So something to think about.
Yes. Mm-hmm. So far this is all resonant excitation.
Yeah.
So,
it's,
but,
it's neutral dot, so there's no.
Yeah. Mm-hmm. Yeah. But you're right. If you go for in the trion state for the Raman excitation, this could work. Yes. Mm-hmm.
Have you got sort of a scheme for the entanglement generation? I mean, so if I understand things right from quantum dot people at ETH, then they need to have a splitting of bigger than 2 gigahertz or something like that. And is there a prospect of having that in the utopian line? Or?
No, but I think one can shift that around with AOMs. So I mean, the two photons that come out, they have different polarizations and different frequencies. You should tennis beam splitter shift the frequencies to be resonant. I think this should be possible. The problem is more that in the dots, they still don't yet have the single shot readout. So even when they do the spin-photon entanglement, they don't have a single shot readout for this. And this could be a bottleneck here. So.
All right. Well, thank you. Thank you,
Okay,
Michael,
thanks.
again.